So, good afternoon, everybody. So I'm going to talk about black holes versus wormholes, scattering, absorption, and quasi-bound states. And these works were done in collaboration with Haroldo Lima Jr. and Professor Luis Crispino, and they were published in PRD and EPJC. So in recent years, we have seen the first image of the compact object that is in the center of our galaxy. And we have also seen the first detections of gravitational waves, and since then we have seen a lot of other observations of gravitational waves. And most of these observations are consistent with the collision of two black holes. However, the standard black hole solutions that we know from general relativity, they are cursed with singularities in their center. So at the singularities, we know that the physical quantities goes to infinity, and we don't really know what's happening there. But Penrose showed in '65 that we can form this kind of solutions of these black holes and these singularities through the collision, through the collapse of matter. And so what do we do with this? So one thing that we can do to kind of to accept these singularities is we say, okay, so we have the singularities, but they are always hidden by an event horizon. So anything crazy that happens near the singularity is not going to affect what is in the outside world. But for some people, that's not enough. So we can consider then a solution that has an event horizon but does not have a singularity. So the first solution of this type was considered by Bardeen, and since then, which is a regular black hole, and since then we have a lot of different regular black holes, as the one, as for instance, the one that Marco told us about. So we can also have other kinds of compact objects that lead to the similar emissions of gravitational waves and also to similar image, so similar shadows. And one interesting kind of compact solution is a wormhole. So these are very popular in science fiction because you can travel from one universe to another, or you can travel to a different point of the space-time of the same universe. And we have a type of black hole associated with the Schwarzschild solution. However, this Schwarzschild wormhole, it's not traversable. And this happens, and the reason for this, or one of the reasons for this, is because this wormhole is not static, it's dynamic. So we have the throat, as the time passes, the throat expands and contracts. And this process happens so fast that even a photon does not have enough time to cross from one universe to the other. Conditions for having a traversable wormhole were considered by Morris and Thorne in '87. And they found they found solutions for this kind of traversable wormhole, but they found that in order to form these wormholes, you have to have you need some type of exotic matter. But there are some recent works that show that you can have within GR traversable wormholes with reasonable matter. So you don't need exotic matter. You can form this kind of wormholes with regular matter. So the spacetime that I will consider is one that was proposed by Simpson-Visser in 2019. And it's interesting because it's a spacetime that by changing this parameter A, we can have a Schwarzschild black hole for A equals 0, a regular black hole for A between 0 and 2n, a one-way traversable wormhole for A equal to n, and a two-way traversable wormhole for A greater than 2n. So this is a nice space-time to kind of try to study these different situations at the same time and try to compare these different situations. So I'll start by talking about the absorption in this spacetime. So we will consider a massless scalar field. And basically what we have to do is solve this radial equation. And we have this effective potential. And here we plot this effective potential in the left side for the black hole case and the right-hand side for the wormhole. So for the black hole case, we see something that we are used to when we consider black holes. So we have a maximum. So this potential goes to 0 at infinity and at the horizon, and we have a maximum for this effective potential. As we increase the angular momentum, this maximum gets higher. So this effective potential gets higher. But when we look now to the wormhole solution, we see that depending on the value of the parameter A, we can have a potential well centered at the throat of the wormhole. So the throat is located at r equals 0, and we have this minimum at the throat. As we increase the value of A, so for A equal to 3n and above, this minimum disappears. So this red line is for A equal to 3n, so now we don't have a minimum anymore. So now for A equal to 4n, we can see that now we have a maximum located at the throat of the black hole, of the wormhole, sorry. So in order to solve, to find the absorption cross-section, we need to solve the radial equation subject to some boundary conditions, and we'll have to consider different boundary conditions for the black hole branch and for the wormhole branch. So for the black hole branch, we consider regular E-mode, so we have an incident wave coming from past no infinity. Part of this wave is transmitted at the horizon, so it's absorbed by the black hole, and part is transmitted to future new infinity. So part is scattered back to infinity. Okay? When we consider now, okay, so just let me talk about this. So here we impose the conditions at the horizon where we have the transmitted part of the wave, and here we impose the conditions at infinity. So we have the incident wave and the reflected wave. Now, when we consider the wormhole branch, now we impose the boundary conditions at plus infinity and at minus infinity. So now we have an incident wave from past new infinity. Part is transmitted to future new infinity 2, and part is reflected back to future new infinity 1. Okay, so we are going to solve these equations numerically for all the range of frequencies, but first we will consider also some asymptotic limits. So for the high frequency regime, these scalar waves, the behavior of the scalar waves approach the behavior of no geodesics. And these no geodesics are subject to this effective potential, which we plot here, and they are very similar in form to the effective potential that I've shown before. So here for the wormhole branch, we also have this minimum located at r equals 0. And now we see that for this case, we have two maximums. So we have two radius for the photon orbit. In this case, the absorption cross-section is given by the capture cross-section, so it's given in terms of the critical impact parameter. For A below 2m, we have this value for the photon orbit, but now for the wormhole branch, we have, as I showed before, we have two different photon orbits, And for A above 3m, let me just go back. So for A, for 3n and above, we don't have more a minimum at the throat of the wormhole. Now we have a maximum. So now the photon orbit is located at the throat of the wormhole. So we can have these 3 different solutions, or 4 different solutions, 3 different solutions for the photon orbit. But mainly the ones that are going to matter to us are these 2. So for this, we have these 2 different solutions for the photon orbits. And associated to these values of radius, we have different values for the impact parameters, and we find then the solutions for the capture cross-section. Okay, so we can have these 2 different solutions. So for A below 3m, we have the same capture cross-section that we have for the Schwarzschild solution. But for A above 3m, we have a different capture cross-section that now depends on the parameter A. So for the high frequency limit, we can also try to find a better solution. So we can look for a solution that reproduces the oscillating behavior that we observe in the numerical solution. So we can do this by considering the work of De Canini and others. And we can show that we can write the high frequency absorption cross-section as a sum of the capture cross-section plus an oscillating term that we write in terms of characteristics of the photon orbit. And this oscillating term is written in terms of this sinc function, which is a sine of x over x. We also have an approximation for the low frequency limit. So in this regime, for the low frequency regime, we have a very general result by Das and others that says that for static spacetimes, the low frequency limit of the massless scalar field is given by the area of the black hole. So this applies also to our case. Okay, so now we can solve the radial equation numerically subjected to the boundary conditions that are shown you. And we compute the absorption cross-section. So this is the total absorption cross-section, which is given as a sum in terms of a sum of the partial absorption cross-section, which is in here. And these are our numerical results. So here we plot a numerical absorption cross-section, and we compare this solution with a sinc approximation. So this sinc approximation is for the high frequency regime, and we see that this sinc approximation coincides with our numerical solutions for mid to high frequencies. So but for low frequencies, it can be very different from the numerical results. But for mid to high frequencies, it gives a very good approximation. So here we plot the total absorption cross-section for different values of A. And mainly what we see here, so this black dotted line is the capture cross-section. And we see that these solutions, they coincide for the low frequency limit. They all go to the same value. And for the high frequency limit, they tend to the capture cross-section. And for the other values of frequency, they oscillate around this capture cross-section. And the main difference between these solutions for different values of A is the amplitude of these oscillations. So as we increase the value of A, the amplitude of the oscillation also increases. Okay, so this is the partial absorption cross-section, which so here we compare the partial absorption cross-sections with the blue dotted line is the Schwarzschild solution, and the black line is for the A equal 1.5. And what we see here is that so mainly the total absorption cross-section is given a sum of this partial absorption cross-section, and we see that each partial absorption cross-section has a maximum for a different value of the frequency. So this is what gives that oscillating pattern that we saw before. Okay, so for the wormhole solution, which is the more different, more interesting case, we see that now for the total absorption cross-section, we can see sharp peaks appearing in this total absorption cross-section. So these sharp peaks are related to this minimum that we have now in the potential. So now with this, so now in this region we have some trapped modes. So and we can find the frequency associated with these trapped modes. So we computed these frequencies, and here these lines that appear here are given are the real part of these trapped modes that are presented here in this table, and they have a very small frequency part. So this which shows that they are very long-lived modes. As we increase the value of A, these sharp peaks become less pronounced, and for A equal to 3m and above, we don't see these sharp peaks anymore. These sharp peaks also appear in the transmission coefficient, and by considering an approximation done by VIII for the nuclei scattering, we can also relate these peaks in the transmission coefficient with this frequency of these resonant modes. And we see that these peaks appear when the real part, when the frequency approaches the real part of these resonant modes, and the imaginary part is related to the form of these peaks. Okay, so I will also talk very quickly about the scattering. But as Marco has already told us a lot about this, so I'm going to pass very fast by this part. So we are going to consider the differential scattering cross-section. So basically we have an incident beam, and we want to know how much of this incident beam is scattered through a solid angle. And in order to do that, we compute this differential scattering cross-section, and we have to find this scattering amplitude, f theta. But this solution, it's very poorly convergent. So instead of this, considering this, what we consider is this reduced series. Okay, so we will consider also the classical scattering solution. So if we consider a geodesic passing close to a compact object, then it's going to be scattered by some angle that I'm calling key. But due to the presence of the photon orbit, this geodesic can spiral around the black hole or around the compact object many times before being scattered to some angle. So you have to consider this sum in this classical scattering. We have to consider this sum. Okay, so this is a plot of the classical scattering cross-section. So it goes to this classical scattering cross-section, explodes to in the forward and the backward direction, and we see that there are some difference for when we consider different A. There are some different that are most pronounced around 150. So if we consider only the geodesic approximation, then we are going to leave behind some of the effects that appear because we are dealing with scalar field. So some effects that are related to waves. So in order to consider that, we can consider the semi-classical effects. So basically, we can have waves that have different impact parameters that are scattered to the same angle, so these waves will interfere. So this will give us also an oscillating pattern in the scattering cross-section. If we since we have the photon orbits, now we can have waves that are scattered to large angles, so angles close to pi. If we consider these waves that are scattered close to pi, then we can have the glory effect, and we can consider this expression for the glory effect. So for the scalar case, this solution will give us a bright spot in the backward direction. Okay, so in here we plot some of the parameters related to the geodesics. In particular, this expression, which is this red line, is mainly the amplitude of the glory effect, and we see that as we increase the parameter A, this amplitude also increases. So we can expect a higher intensity of the glory effect for larger A. So here we plot the numerical solutions for the scattering. So they are very similar. In general, the behavior is very similar when we consider a Schwarzschild or a regular black hole. Here we compare the numerical solution with the geodesics in the glory approximation. Okay, so here we consider the wormhole case. So now we see that the width of these solutions changes as we change the value of the parameter A. And we can also see in here in general more differences between these differential scattering cross-section. Okay, so so this is what I wanted to show you while I still have some time. So we saw that for the absorption cross-section, due to the presence of this minimum in the potential, we have some quasi-bound states that lead to the sharp peaks in the absorption cross-section. So we wanted to know what happens in the scattering case when we consider these resonant states. So here we consider the differential scattering cross-section for resonant solutions, which are these black lines, black curves, and we compare these cross-sections with other cross-sections for similar values of frequency. So with a frequency omega plus, which is slightly higher than the resonant frequency, and omega minus, which is slightly smaller than the resonant frequencies. What we see is that in general, these differential cross-sections for the resonant case seems to be smaller than these other closed frequencies. Okay. So in general, what we saw is that the behavior of the absorption cross-section and the scattering cross-section for the black hole branch of the solutions is very similar, but when we consider the wormhole case, we see resonance peaks that appear in the absorption cross-sections that are related to these quasi-bound states that are trapped in the potential well. And for the differential scattering cross-sections, we see that this leads also to a lower differential scattering cross-sections for these resonant frequencies. Thank you.